Hello everybody. In today's video we'll be talking about linear regression model. So first of all it should be clear to you that what is a regression problem. So regression problem is it is a supervised problem, like you have supervised machine learning problem. Okay, supervised machine learning problem means you have labels attached to your data instances, and then your data, like you have something like this: x is your features, y is your target value, and y is in a continuous set, right? So y is not taking discrete values, it is taking a continuous it is taking values in a continuous set. For example, you can have y as prices of the houses. Okay, so it means that it can be any a real number, it can be something like speed of a vehicle and something like that, right? So basically what we have here, suppose I have a data where corresponding to, say, number of rooms in the house and living area, right? So I have price of the house in rupees, right? So for example, we are saying if there are 2 rooms in the house and the living area is, say, 1000 square feet, okay, square feet, then we say that the price of the house is, say, 30 lakhs, right? And then you can go for 3 rooms and then maybe 1500 square feet area, and the price of the house is, say, 50 lakhs, and so on, right? So you can also have something like 55.2 lakhs, okay, and so on. So you have something like this is your data, right? Okay, so now this is your, these two are your features. So this is my feature vector. So this one is this is my feature vector, right? This one only up till here, and this is my target value, right? Okay, so now the idea is that we will, if I give you a new, a set of features, for example, if I give you that for, say, 1 room and area of living area is, say, 100 square feet, what will be the price? What is the price? Right, so that is my question. Right, now if you belongs to like maths background, then you know that this is nothing but an interpolation problem. So that is what we are trying to do here, regression. That is why the name linear regression, right? So let me just give you the formal notations first before continuing, right? So what we are going to do here is, for our set of features, I will say I have n features, okay, and suppose in your training data there are m examples, right? So training data means number of examples on which you want to train your model. So what I have, I'll denote like this. This is my first data set corresponding to features, and this is the corresponding output value label attached. So this is actually containing how many values, n features are there. So this is x1 1, then I have x1 second feature, and so on, x1 nth feature, right? Similarly, we denote it like, we make it as a column vector, right? And then I have the second example. So I have the first feature of the second example, second feature of the second example, and so on, nth feature of the second example, and then I have my corresponding label, and then I have x3, that will be x1 3, x2 3, and so on, xn 3, right? And then I have y3, and so on. I have my nth, I have total m examples. So you can see that we have total of m examples. So I have my mth example as mth example first feature, then mth example second feature, and so on, mth example nth feature, okay, and the corresponding you have a label which is yn. So does that make sense? So this is the kind of thing we have. So these are our labels and this is our feature set. Okay, great. So we want to know a model. We want to know a model which tells us the value of y when these n features are given. So let us, this is our model design. So this is my choice, right? I can design many models, but for linear regression, a model looks like that you have y as a linear function of x1, x2, xn. So this will be some theta naught plus theta 1 x1 plus theta 2 x2 plus so on plus theta n xn. So this is my model choice, right? Here theta is are to be calculated. Here theta is are to be calculated. Now the question is, how do we calculate these theta i's? How do we calculate this theta i's? How do we calculate these theta i's? That is my question. But before that, let us write this model in a simpler form. So what I can do is, I can write it like this. Can I write it like this? Theta naught, theta 1, theta 2, theta n, a vector, and then another vector. So what I'm doing, I have x1 with theta 1. With theta naught, I don't have anything. I'll put a 1. So I'll put 1, x1, x2, xn, right? And this is your x vector. Call it your x vector and call it as theta transpose, because we are dealing with column vectors. So theta is a column vector containing theta naught, theta 1, theta n. So note that this is n plus 1 rows and 1 column. So this is also n plus 1 rows, 1 column, right? So what I'm doing here is, I'm writing my model as theta transpose x, where both theta as well as x, both theta and x, they are n plus 1 size n plus 1 row vectors, and in case of features I have added an extra 1 in the beginning to make it n plus 1. Okay, so this is my model. So I hope that makes sense. Now let us see how we can find out our theta i's. How to find out theta i's? For that, what I am doing here is, I already know m examples, right, from my training data, from the training data. So what I'm doing here is, I'll say, okay, corresponding to the first set of features, this is my predicted value of the output. What is the predicted value? Theta transpose x1. Okay, and this is my actual value. What is the actual value? Actual value is y1. This is the data given to us. So we can look for the error. So error will be theta transpose x1 minus y1. Okay, and similarly, corresponding to, this is my features set, and this is example 1. Similarly, for example 2, I have my feature vector as x2. So my predicted value is theta transpose x2. The actual value is y2. So the error would be theta transpose x2 minus y2, and so on. You can keep on doing this for all the examples given to you, and for the mth example, you have your feature set as xm, predicted value will be theta transpose xm, actual value will be ym, so the error would be theta transpose xm minus ym, right? So you kind of, you create a table where you have all your feature set, you have all the predicted values and the actual values, and then you calculate the corresponding errors. Now we know that we don't care about the sign of the error, we are interested in the magnitude. So what we do, we square them, we square these errors. Okay, you can also take modulus, but taking square is better for further analysis. So we can take the squares and then add. So if I add all these quantities, so can I write it like this? I from 1 to m theta transpose xi minus yi square, and for simplicity I am dividing with 1 by 2. I am dividing with 2, so I have 1 by 2 in the front. So you'll see that in some books they divide with 1 by 2 m and so on. There are so many things going on. So this is the error. We call it as cost function j theta. This is called cost function j theta. Right now, what you have to do, now we say that our aim is to keep the errors to minimum possible values. Okay, so what you can do is you can do the derivative of j theta. So choose theta which minimize j theta. So that is one thing, right? So from calculus, that is why they say that for machine learning you need to know calculus first. So from calculus, from our calculus study, from our calculus course, we know that the values of theta 1, theta 2 and theta n which minimize j theta are obtained from, what you do, you put the derivatives equal to 0 from the following equations. So you put the derivative of j with respect to theta 1 equal to 0, then derivative of j with respect to theta 2 equal to 0, and so on, derivative of j with respect to theta n equal to 0. Okay, that is good. We can do that. Now, if you look at these quantities, there are matrices involved, right? So there are matrices involved. You can see that this is, you can try to find out, for example, this is a vector. Okay, this is also a vector, right? If I try to differentiate it with respect to theta 1, theta 2, it is not that easy. But still, what we are going to get if we do so we will get that your theta is x transpose x inverse x transpose y, where x transpose is a matrix created as follows. So what we do, we take our first feature set, we take the transpose and put it in the first row. Then I take my second feature set, take the transpose and I put it in the second row, and so on. I take my mth feature set, take the transpose and put it in the mth row. So this is a design matrix. We call it as design matrix. So you see what we are doing here. How many elements are there in the first row? So x1 contains n, there are n features, but we are also adding 1. I told you here that we have to add an extra 1 here, right? Yeah, we are adding this extra 1. This is called bias, right? So we are also adding a bias. So that is why how many rows are there in the first, how many elements are there in the first row? There are n plus 1, n plus 1. So number of columns are n plus 1 and number of rows are m. So you create a design matrix, and we will do the derivation in another video. Derivation will be covered in another video, that how from here you reach here, okay, will be done in a separate video because it's a long process of calculations in a separate video. Fine. So you get your thetas, right? Okay, so these are called normal equations. These are called normal equations, right? So we have our solution from the normal equations, right? So this is the one way of finding out your thetas given your model. And what is y here? Y is your vector containing the labels of your training data, right? So this is your y. So I'll give you an example. We will do an actual example where you will be able to understand what I'm talking about, and then we'll see that this is not a very practical model. Calculating the normal equations, calculating the value of theta from normal equations. Why? Because you look here, you have to invert a matrix, right? And this somehow relates with the data size you have in your training set. So if your data size is very huge, so this matrix is going to be large, and inverting large matrices is a very tedious task in mathematics. So, and we usually avoid it. So in the next video we will be looking at that how can we avoid calculating theta with the help of normal equations, right? But here we'll continue with one example where we will be calculating our thetas using this normal equations, right? So here I have this data set x1, x2, y. I have -1, 5, 1, 5, -2, 2, 4, 1, 3. So this is my data set, and the question is fit a linear regression model. Fit a linear regression model. Okay, so what you will say, you'll say, okay, when I'm fitting a linear regression model, so I have this thing, right? If I'm fitting a linear regression model, so I have y equal theta equal to x transpose x inverse x transpose y, right? Simple. So let us construct our x. X is the design matrix. So you have the first feature set, but you have to add a bias term. So write your first feature set, and then the second feature set, add a biased one, and then add your second feature set. And similarly for the third one, you add a bias one, and then you add your 4 and 1. So this is x. And what is y? Y is simply your labels 1, 2, 3. Now what you have to do, you have to do x transpose x. So that will be, take the transpose of this matrix 1, -1, 5, 1, 5, -2, 1, 4, 1, and then multiply with the same matrix 1, -1, 5, 1, 5, -2, 1, 4, 1. If you do so, do the calculations, you will get this is equal to 3, 8, 4, and then you have 8, 42 minus 11, then you have 4 minus 11, 30. So this is my x transpose x, and then x transpose x, you calculate the inverse. If you calculate the inverse, inverse calculation is little bit time taking process. You can use a calculator if you like. So the inverse matrix comes out to be this. I'm writing it here. You can do it for your own sake of understanding that how we are calculating the inverse of the matrices. 121 65 upon 121, and then you have minus 256 upon 121, 65 upon 121, and then you have 65 upon 121. So this is my x transpose x, and then I can also multiply, I have to multiply with x transpose y. So if I do so, x transpose y, okay, so we can calculate x transpose y, or what we can do is we can just do all the multiplications together. So finally our theta is x transpose x inverse x transpose y. So that means this matrix here, then x transpose, which is 1 1 1 minus 1 5 4, 5 minus 2 1, and then your y matrix, which is 1 2 3, and you do all the multiplications, and this is what you are going to get. So this is equal to minus 51 upon 11, 16 upon 11, 280 upon 121, right? So that means my y looks like, this is my theta naught, this was the actual case, right? So here this is my theta naught, this is my theta 1, and this is my theta 2. So this is minus 51 upon 11 plus 16 upon 11 theta x1 plus 280 upon 121 x2, right? So I want you to note these points, right? That okay, we can always create a model. This is simple, right? But you have to understand that we have only two features here. You had only these two features. So for me, writing the normal equations were not that hard, but still calculating going from here to here was quite hard when I did the calculations with hand. So obviously, and in real life examples, when we are working on real data, these x1 x2 xn, the number is huge, right? So we don't want to invert matrices with that size. So that is why calculating the values of theta from the normal equations is not a practical approach. So in the next video, we'll be going to work on gradient descent method, which is actually used for this kind of regression problem. So idea of regression problem is that you are trying to, model, you are trying to make a model like this, a linear model, right, which is giving you your output. This is your output here as a function of linear function of the inputs like theta 1 and theta 2. Okay, thank you for watching this video. Please do share and subscribe. Bye, have a nice day.